Hey folks, it's Mr. Woodward talking about conservation of momentum. So what is conservation of momentum? Well, let's jump in. Starting over here, the law of conservation of momentum states that the total momentum before and after a collision or explosion remains the same within a system of objects. So it doesn't go up or go down. Since momentum is neither created nor destroyed, it's transferred from one object to another or shared between objects through the action of forces as described by Newton's laws of motion. So you may be wondering, how can the momentum be conserved when a collision or explosion causes the mass or velocity of the objects to change? Well, the increase in momentum of one object will always equal the decrease in momentum of the other, so that the total always remains the same. The law of conservation of momentum can be hugely helpful for solving problems involving collisions between objects or the explosion of an object. So we're going to take a look at three examples of conservation of momentum called elastic collisions. That's one way in which objects can interact. Second is inelastic collisions, and the third is during explosions. So let's take a look at elastic collisions. During elastic collisions, objects bounce off of each other, such as when two bumper cars or two billiard balls collide. The total momentum of both objects before the collision will be equal to the total after. So for example, if you've got, if you're playing a game of pool and you've got a ball moving to the right and another ball moving to the left towards each other at the same time, then after they collide, they will change direction. If this ball has more momentum, it will continue moving to the right, and this ball will change from going to the left to moving to the right. And so there's a governing equation when objects are bouncing off of each other, which is that the mass and velocity of the first object over here plus the mass and velocity of the second object here will be equal to the mass and velocity of the first object after the interaction plus the mass and velocity of the object, the second object after the interaction, so that the total remains the same. So we're saying that the momentum of both objects here before the collision is going to be equal to the momentum of both objects here after the collision. Okay, what about if the objects don't bounce, but what if they stick to each other? Well, that would be called an inelastic collision. An inelastic collision is when objects stick to each other or embed in one another, such as when football players tackle, when a bullet hits a wall, or when two balls of clay collide. Since the two objects become a single combined object after the collision, the conservation of momentum equation simplifies as shown below. So we get this new relationship here. So for example, now we've got object one, which is moving to the right with a velocity, and object two is still moving to the left. But now, after they collide, they stick together, and they become a combined object over here moving with a common velocity. And so we have the same equation as before, where we have the momentum of the first object plus the momentum of the second object, but now it's going to be equal to the combined momentum of both objects after the collision moving with a common velocity. So this is actually a simpler situation than in an elastic collision in type 1. So in an elastic collision, which is what we just looked at here, the objects, two objects become one. Well, the opposite is also possible. What if one object became two? Well, that would be an explosion. During an explosion, a single object separates into several unique objects due to the force of the explosion. This is similar to an elastic collision in reverse. So what do I mean by that? Well, here we've got one object, a big mass, and it's attached to a fuse, so it's going to explode. So the total momentum before the explosion is mass 1 plus mass 2 times the velocity that it's at. If it's at rest, it has no velocity, therefore no momentum, or it could be moving, and therefore it would have some initial momentum. But then after it explodes, it separates into two pieces. One piece is going to move this way with leftward velocity, and so we could describe the momentum as its mass times its velocity. The other piece is going to move to the right with rightward velocity here, and so it has momentum to the right. But the total momentum of both of those pieces, of both of these pieces, is going to be equal to the original momentum of just this piece to begin with. Let's take a look at some examples of this in the next video.